Okay. So I'm going to talk about Frobenius structure of the statistical manifold. Yeah, so basically, this is subject of information geometry. So a summary is the following. So I will talk about some basic concepts like dual connections and Hessian matrix. And also the flat connection actually is related to the famous Chern conjecture. And also the Hessian matrix. And the special Kahler matrix is a special type of Hessian, the special Hessian matrix. And the statistical manifold, you will see it's a generalization of the Hessian manifold in some sense. And also Frobenius structure, basically we assign some product structure to the statistical manifold. Okay, so the definition of dual connection is the following. So we have an affine connection. Yeah, we do not assume it's a Alekseevsky-Cortes, but I only assume it's affine. And the dual connection is defined to be the following connection d bar, and they satisfy this equation. And you will see that if the d is the Alekseevsky-Cortes connection, then this equation, if we just use d hat, the Alekseevsky-Cortes connection for both d and d bar, then this just means the compatibility of the connection with the Riemannian matrix. Yeah, in other words, it means that the Alekseevsky-Cortes connection of a Riemannian manifold is self-dual. The flat connection, by definition, we need to assume that the curvature and also the torsion, they both are free, and then I say that the affine connection is flat. Yeah, it's not enough to assume only the curvature is zero. We need both. So this is the well-known. The third one is the well-known fact that a affine connection is flat if and only if in each point we can find a local coordinate such all the Christopher symbols vanishes. This is so we need to solve a partial differential equation to arrive at this conclusion. So flat connection is a very important concept in many subjects of geometry and also in physics. So we have this moduli space of all the flat principal G bundles over a smooth manifold. So we have this moduli space. So actually you can find that this flat connections on this G bundle are in one-to-one correspondence with the homomorphism of the fundamental group to the group G, and up to the quotient of G. And so we see that the moduli space actually is also compact when the surface the surface is also compact. Yeah, actually this moduli space is used in the formulation of the so-called the Witten-Wallinder formula, and actually physicists could give very interesting formulas about those intersection numbers on this moduli space. Bianchi identity, we know they are famous in Riemannian geometry, but here I just point out that actually we only need this connection to be torsion-free. Yeah, we do not need it to be compatible with the Riemannian matrix, and then we still have the first and the second Bianchi identity. And yeah, so we do not actually need this compatibility actually. This is a definition of affine structure. Okay, so affine structure just means that when the transition function of all the local coordinates of the manifold, they are just given by affine maps. So A is general belongs to the general linear transformation, and C is a vector. And an interesting fact is that affine structure is in one-to-one correspondence with flat connection. Yeah, so yeah, so I think this is interesting. So I think in some physical study, in some mathematical or physical study of the mirror symmetry, people usually study integral affine structure. It means that A belongs to GL and Z, and C belongs to CM. So we can have many constructions of mirror symmetry starting from the integral affine structure. And this Chern conjecture is about flat connection or about affine manifold. It just says that the Euler number of a closed affine manifold is 0. So we know that when this flat connection is simply the Levi-Civita connection, then the assertion followed from the Chern-Gauss-Bonnet theorem. But in general, this is open. So, but in general, Chern conjecture is still open. So we have some special cases like when the manifold and affine structure, the affine connection is geodesically complete, or when we have this this manifold is a surface. And also more recently, Professor Feng Huitao and Wei Ping Zhang, they proved some counting formula for the Euler number of a flat vector bundle by using multi-equivalent formalism, and they have a new approach to the Chern conjecture. So this is a concept in information geometry. So we have a connection and a Riemannian manifold, and the connection and the matrix are called Cortesi coupled if they satisfy the following Cortesi equation. Yeah, so you see, we just interchange x and z, interchange x. So x, y, z are all the vector field. Yeah, so of course x, y are symmetry. Yeah, so in other words, Cortesi equation guarantees that this 0,3 tensor nabla G is a totally symmetric tensor, right? Totally symmetric 0,3 tensor. Yeah, this is a very important concept in the in affine differential geometry and also in information geometry. So we have this connection and it's dual. Then actually there are curvature tensors and sorry, this should be torsion tensor. They satisfy these equations, and I think these are well-known facts in affine geometry. So these are also the conclusions, like the torsion tensor is equal if and only if nabla G is Cortesi coupled, and nabla is curvature free means the curvature tensor equal to 0 if and only if its dual connection is also curvature free. Yeah, so I think 1 and 2 follow directly from the above two equations, and if this affine connection is both curvature and torsion free, then the dual connection may be not flat, and it's flat if and only if it's Cortesi coupled, right? So, also you can see that Cortesi coupled, nabla G is Cortesi coupled if and only if nabla bar G is Cortesi coupled. Yeah, so this should not difficult to see. I think Hessian manifold is kind of important because it's also related to the affine to the affine structure. Okay, so we start with a so this just means we start with a affine manifold, right? So we have a manifold with a flat connection, and a Riemannian matrix on this affine manifold is called Hessian. Just means that this G could be locally written in terms of the Hessian matrix of some function on this affine coordinate. Yeah, so we have this restriction that this phi, we write this G in terms of Hessian of some function only on the corresponding affine coordinate. So we know that a flat connection is in one-to-one correspondence with the affine structure, right? But if we do not use affine coordinate, then maybe we do not have this form, right? The matrix may be not in this nice form. So the following conditions are equivalent. So G is Hessian matrix, just means this Gij, the K, the xk, I and K, or J and K could interchange, right? Or this nabla G is Cortesi coupled, and its dual connection is flat, right? So these are the equivalent definitions of the Hessian matrix. Hessian matrix also means the so-called dually flat connection. Yeah, so I will explain this when we talk about the statistical structure. So Legendre transform is important in convex analysis or in convex geometry. Yeah, so if we have a Hessian manifold and we have a Hessian potential, then we have the Hessian potential for the dual. So sorry, this nabla should be bar. And yeah, so sometimes people use nabla star to denote the dual connection. Here we use nabla bar. And this is the prime is the affine coordinate correspond to the dual connection. And actually the Hessian potential of these two dual connections are related by the Legendre transform. Yeah, they are related. So more explicitly, you can just use this one. The coordinate, the affine coordinate are related in this simple form. So when the Hessian manifold is compact, actually we have some trivial topological consequences, like its universal cover is a convex domain. I think this is a theorem of Japanese mathematician Shima. And its fundamental group is infinite. Yeah, I think this is clear because the convex domain is non-compact, right? So the fundamental group should be infinite. And also, if the connection preserves the matrix volume form, then we could conclude that this G is flat and the nabla is just a Alekseevsky connection. Okay, so this is just some restriction on the compact Hessian manifold. So the study of Hessian matrix, it's kind of real analog of Kahler matrix, right? So first studied by Chern and by Hao, Shima, and also Chern and Yao. Yeah, sometimes people call it like a real, call it like a Kahler, call it a affine Kahler matrix by Chern and Yao. They also proved the analog of Calabi conjecture for the real Hessian manifold. And this Hessian matrix or dual flat connection structure also found on the smooth families of probability distributions. And they are the first batches of examples of the Hessian manifold or actually the most important examples of in the information geometry. And they have so we can have important application of information geometry in statistics and also in the machine learning with the study of dually flat connection or more generally statistical structures. So this is the example of Hessian manifold. Yeah. So actually you will see that. Yeah, so let me just review this definition of the probability distribution. So we have this parameters are actually given by x and theta. Yeah, so theta. So yeah, so the manifold parameter actually is just this theta. So theta lies in a domain of Euclidean space, and this probability distribution is of this form, right? And if I write log p as L theta, then the well-known, the famous Fisher information matrix is given in terms of this expectation, right? Expectation, and we can prove that actually this Fisher information matrix is affine. Is actually on Hessian matrix in the affine coordinates. Yeah, it's not affine. Yeah, so in other words, we will see that. So we can have this affine coordinate, and actually you will see. So by definition of Hessian, its dual connection should also be flat, right? And this could be easily proved. Yeah. So actually, this is a very important example of the information geometry. So the Hessian matrix also has very wide connections to differential geometry and to physics. So for example, we see that if I look at the Hessian matrix, so this F is just the Hessian potential, and the Riemannian matrix is GIG, right? It's the Hessian matrix, and we can compute it's a Riemannian curvature tensor. It's given by the third derivatives of the Hessian potential F, and so actually the flatness of this Riemannian matrix is simply governed by the WDVV equation. In other words, it just means G is flat if and only if it satisfies this WDVV equation. And in this bracket, you see that we only interchange this I and J, right? So I keep all other indexes and I interchange index J and I, right? So when I do the summation PQ, so I get 0, and this is called the WDVV equation, and it's given. It's actually discovered by 4 physicists working in string theory. Yeah, so let me give another more famous example of the WDV equation, and this is actually the original version of the WDV equation, and they come from the study of the cohomology, the quantum cohomology. So we have this projective manifold X, and look at its cohomology. This is basis beside this unit 1, and define a generating function, and this is the usual way people the usual way people in physics important invariants, they write them in terms of generating function, and these are called the coefficients are called Gromov-Fit invariants, and they are just some modular space and aimed to counter class beta curves on the projective manifold. DVV equation in this case, it just says that the Gromov-Witten generating function, right? If I take its third derivative, and they satisfy this equation, and actually, yeah. So this is slightly different. So one have just in the Hessian matrix. Okay. So this WDV means we have an associative. So we just use this third derivative to define a product on the cohomology in the cohomology, and WDV exactly means this product is associative, and activity is the that I so about when I talk about Frobenius. Okay, and this is a characterization of Hessian matrix. So basically, this it used the WDV equation, and the Totaro proved that this Hessian matrix, and in the domain U, okay, in this domain U, cool. But if and only it's a restriction to the hypersurface. Yeah, this hypersurface is one dimension smaller than this, right? So it's n minus 1 dimensional, and has constant sectional curvature. Right? Yeah, I think this is interesting. So it connects to the Hessian matrix. So yeah, so you will see that the flatness of Hessian is important. It means that we the Hessian matrix that we can have Frobenius structure. So this is very important and a special case of the Frobenius manifold. Yes, we'll talk about Frobenius. Yeah, so this is this is a theorem of we have a pseudo matrix. Then that gives a tree, right? From WAP to this domain U. So next I will talk about a special kind of this Hessian manifold. It's called a special Kahler manifold. So this is the definition of the exterior derivative, right? And so we can take a derivative over so not just over forms, but maybe on form with a tensor with sections on the tangent bundle. Yeah, I think this is standard, some standard definition. Okay, so yeah, so the importance of in this definition is that this D should be flat, right? when D is flat, then it just gives a exact yeah. So we have our sequence. So a special Kahler manifold. So it's a Kahler metric and a Kahler form, and also a flat connection. This flat connection is parallel with also this exterior derivative on the complex form is equal to 0, and in fact, this null condition, the grand derivative of G is totally symmetric. Yeah, so we know that totally symmetricness of this nabla G just means that this M nabla G is a real Hessian manifold, right? So yeah, so basically the condition 4 is just mean have a real Hessian manifold when we consider this Kahler metric to be Riemannian manifold, right? So examples of special Kahler manifold include the moduli space of deformation of the Lagrangian submanifold in a hyper-Kahler manifold, and also example of the base of a complete integrable system, and also the moduli space of Calabi-Yau threefold is a so projective is slightly so basically our definition gives a so our definition of special Kahler is so-called affine, and we can also similarly define projective special Kahler manifold. And the basic properties that we know of is by Professor Lu Ziqing. He proved that any special Kahler manifold has non-negative rigid curvature, and its scalar curvature is identically 0. And then the curvature tensor also vanishes. Right? It's a flat. Right? It just means when scalar curvature is 0, it's flat. And also the special Kahler actually. They are interesting only in the local case, right? So when we consider a complete special Kahler, it must be flat, so it's not interesting. Yeah, but when we call, there are many examples of special Kahler manifold. And this is the so-called R-map, and this is also I think this construction also from physics, from physical considerations. So like we have a manifold and a connection, and we have a neutral complex structure. We have a flat connection, then the actually is a very natural complex manifold. Right? So we can have this complex structure just given by using the affine coordinates. And this Riemannian matrix on the base manifold induce a Hermitian matrix on the tangent tangent bundle, right? And we can show that G is Hessian if and only if this G nabla is Kahler. And Zhang and his postdoc Ken studied when we consider a pair of dual connections, and they call them so-called statistical mirror pair. Yeah, I think they look at their some properties and the connections. Yeah, I think there are some interesting properties contained to compare their geometry. Okay, so special real manifold. Special real manifold. Okay. Yeah, it just means that when we have this so when we have this M nabla G, and this is the special so we have a Hessian manifold, and we map it to a Kahler manifold on the tangent bundle, right? On tangent bundle, and Alekseevsky-Cortes, they observed that when this M nabla G is a so-called special real. Special real means it's Hessian, and also this nabla G is not just totally symmetric. It is nabla parallel. It just means if you take nabla to nabla square G is just equal to 0, right? Nabla square G is equal to, and this is called a special real. And they proved that this RMAP takes a special real manifold to special Kahler. Yeah, in general, it maps hashing to Kahler. It only maps hashing to Kahler. But if we restrict it to special real, and we can see that the domain, the target is the target manifold is a special Kahler manifold. So recently, with Kefeng Liu and Yanhui, we give a new proof of Alekseevsky-Cortes theorem, and we also show that if M nabla G is a special real, then the dual connection is special real if and only if nabla is Alekseevsky, right? So yeah, so this is very restrictive. So in general, this dual is never special real. Yeah. So the only case is that the nabla is equal to nabla bar. Okay, so let me now, so we are going to define this statistical manifold, and this is generalization of a generalization of flat Hessian manifold. Yeah. So when a Hessian manifold is flat, it is a statistical manifold. Sorry. Oh no. Okay. So statistical manifold. Yeah. So I only require both nabla and the nabla bar are torsion free. Yeah. So a Hessian manifold is automatically a statistical manifold. Yeah. We do not need it to be flat. So when a Hessian manifold is flat, it just means this statistical manifold has a Frobenius structure. Okay. But more generally, so I can also define a statistical manifold by using a 1-2 tensor K. Yeah, it just means so if I have a 1-2 tensor on a Riemannian manifold such that this 1-2 tensor, when it combined with the Riemannian matrix, it's totally symmetric in X, Y, Z. Right? Yeah, it's not just symmetric in X, Y, but also in Z. Yeah, so you can interchange X, Z or Y, Z, and you still get the same. Yeah, so these two definitions are equivalent. Yeah, so the proof is not difficult. So this is use the so-called Amari. Yeah, sometimes this totally symmetric tensor is also called Amari tensor. So for a statistical manifold, we can have a concept of so-called K-curvature. Yeah, by definition, we use bracket KK. So bracket KK just means we do the bracket to the K operator, right? So this is a natural definition. And why we call it curvature? Because it has the same properties as the Riemannian curvature tensor. But second Bianchi may not satisfy. But so we have first Bianchi, but not second. Yeah. So these are the familiar properties of the Riemannian curvature tensor, right? So the K curvature tensor also satisfy these. Okay, so I will connect it to the Frobenius structure on the statistical manifold. So Frobenius algebra is a finite dimensional commutative associative algebra. Yeah, so we will see commutative is always satisfied for the statistical manifold, but associativity is a very important property. You know, we need to find a criterion to guarantee this Frobenius algebra is associative. So the following two definitions are equivalent. So we can use either one or two to define this Frobenius algebra. So the first one is just we have a non-degenerate inner product such that GABC is G equal to GABC. Right? So this is a product in the Frobenius algebra. So the linear form is so we can also define Frobenius structure by using a linear form, and from this linear form we can have a inner product, right? We use theta to define this G. Yeah, so one and two are equivalent. So sometimes people like to maybe like to the first definition more. Okay, so Frobenius manifold is a much studied subject in string theory or in the subject of mirror symmetry. So this is a very heavy definition actually. This manifold not only have a Frobenius structure on tangent bundle. Yeah, so it just means at each point of the tangent space, so it's a vector space, we have a Frobenius algebra structure. and it should continue. It should smoothly vary with the point. Yeah, but this is the first property. We also needed the matrix to be flat, and also we should have a so-called unit vector field, which is a parallel on the Alekseevsky connection, and also we should have a 0,3 tensor such that this nebula on C act on C is symmetric. Yeah. So actually, basically, this C is just the right. So this C could be obtained from G or theta by this formula. Yeah. So I think this C is very important in the definition of the Frobenius manifold. Okay. Right. So actually, this is the important observation is that a Frobenius manifold is always a statistical manifold, right? Simply because we can use this totally symmetric 0,3 tensor to define this K, right? So I just define this Kxy to be x times y. So I get a statistical manifold, right? Yeah, but the question is, on the other hand, so I can ask when a statistical manifold is a Frobenius manifold. So sometimes maybe I do not need to like 1, 2, 3, 4. I could relax 1, 2, 3, 4. I only require this this statistical manifold to have a Frobenius structure on its tangent bundle, right? So it's a commutative and associative product on the tangent bundle. Yeah, I do not require 1, 2, 3, 4. Okay, so yeah, so this associativity is very important. We always have this commutativity, right? So if I start with a statistical manifold, I can always define a product by using this K, this totally symmetric 1, 2 tensor. Yeah, the commutativity is very simple. Yeah, but the question is when this product is associative. Yeah, so if this product is associative, then it gives a Frobenius structure on this manifold, right? So we have a very clean criterion. So it simply says that the product is associative, hence gives a Frobenius structure if and only if M has 0 sectional K-curvature. Yeah, so basically the reason the proof is also simple. So when we observe this connection, so actually the proof is simple. And so because we know that associativity is equivalent to the WDVV equation, and this WDVV equation could be interpreted as some kind of some kind of algebra, right? And also in terms of the left multiplication operator. Yes, so I find this follows from a very simple algebra result. Yeah, so at least it gives a connection and also a very simple criteria. And so we have this natural definition, the so-called Frobenius statistical manifold. So it's much weaker notion than the Frobenius manifold, because I only require it to be a Frobenius algebra structure on the tangent bundle. I do not require to have the so-called unit, the flat unit vector field or the matrix to be flat. I do not need that condition. So it's much weaker condition. It's a much weaker concept than the Frobenius manifold. Okay, so non-degeneracy of this K, just to guarantee the Frobenius algebra has a unit. Right, so I need this non-degenerate K. So a Hessian manifold, so we can see that a Hessian manifold is a Frobenius statistical manifold if and only if this Hessian matrix is flat. Yeah, so also the definition of Frobenius statistical manifold is essentially the so-called pre-Frobenius manifold. But in their definition, in the definition of Dubrovin, he used the he usually required this G to be flat, but we can but we do not need this. Yeah, so actually there are many examples of Frobenius statistical manifold have now with non-flat Riemannian matrix. Okay, yeah. So here are some examples of the Frobenius statistical manifold. Yeah, so this is like so these examples are actually not so many. so this is like we do not have many examples of the flat the manifold with a flat connection or examples of affine manifold, right? We actually do not have many such examples. So like in the case of Riemann surface, the only flat manifold or affine manifold is the torus, right? And actually only torus has the Frobenius statistical structure for all compact Riemannian manifold. Yeah. And all orientable three manifold are parallelizable. Means they're yeah. So means that their tangent bundle are trivial, and this already implies they have Frobenius statistical structure. Right? Yeah, we can define a trivial Frobenius statistical structure on the trivial bundle. But any simply connected closed form manifold is not parallelizable, and hence they cannot be Frobenius statistical because we have the following factors. So a Frobenius statistical manifold, if it's simply connected, yeah, it means that if the universal cover is simply connected, then it should be parallel. So yeah, so I will explain this the third point, the third one. So the Frobenius statistical manifold, yeah. So I think this should also so maybe better called the Hessian manifold, because Hessian is the first to study the following situation. So he only consider the manifold with a Frobenius structure, but do not assume flatness of the matrix. And then he proved that the existence of the canonical basis. Yeah, I think this canonical basis, of course, is well known to Brodmann when he defines the Frobenius manifold. Yeah, but Hitchin relaxed the condition of flatness of the Riemannian matrix. Yeah, actually, Hitchin proof is very nice. You just use the semi-simple property of the algebra, right? Do not need too much geometry. Yeah, only semi-simpleness. Okay, yeah. So from this Hitchin theorem, we can have the following result about the properties of the Frobenius statistical manifold. So first, there is a finite covering. Yeah, you can always find a finite covering of the statistical manifold, Frobenius statistical manifold, which is parallelizable. And also a simply connected one is parallelizable, right? Yeah, because a simply connected one, we can always extend these canonical bases to the whole manifold, and this just gives so I mean these canonical bases gives the pointwise linear independent sections of tangent bundle. So tangent bundle should be trivial. Yeah, so any universal cover of the statistical manifold is parallelizable. And when this Frobenius statistical manifold is closed, then so it must have zero Euler characteristic, right? Yeah, so Frobenius statistical manifold is a small subset of closed manifold with zero Euler characteristic. Is a subset. Okay. Yeah, I think 1 and 2 I already explained. But of course, parallelizable manifold may not have Frobenius manifold structure. Yeah, it means, but parallelizable manifold must be Frobenius statistical manifold. But we cannot strengthen it to be Frobenius manifold, because Frobenius manifold we need a flat matrix, right? But like Sophia S3 and S7 are parallelizable, but they do not admit a flat matrix. Yeah, so because their Euler number are not zero, they do not have flat matrix. Hence, they are not Frobenius, right? Yeah. So finally, I give yeah. So somewhat this Frobenius statistical manifold is kind of related to Chern conjecture. Yeah, they have some similarities. Like Chern conjecture said that we have for a closed manifold with a flat Haussian matrix. Yeah. So this just means it's a closed affine manifold. It must have zero Euler characteristic. But in general, this conjecture is still open. So there is another version of Chern's conjecture, which says that a closed-oriented spherical manifold with flat and may have torsion, maybe not torsion-free connection has zero Euler characteristic. As a spherical just means its homotopy group are all zero. Yeah, it means that its universal cover is contractible. It just means the universal cover of a spherical manifold is contractible, right? Yeah, but we know that any parallelizable manifold has a flat connection. Yeah, but in this case also, it's possible that these flat connection may have torsion. Yeah, so so I think to find examples of non-trivial statistical manifold, Frobenius statistical manifold will be helpful to to study Chern conjecture. Well, yeah, because Chern conjecture we need to find more examples of zero Euler characteristic manifold, right? Yeah. I think this is important. Is an interesting concept of the so-called Frobenius statistical manifold. Yeah. So basically, our work is to we have a statistical manifold, and we study when its tangent bundle will have a associative Frobenius algebra structure, right? So we give a criterion using the zero sectional K-curvature. Yeah, I think this is a very nice characterization. So K-curvature, I think it's not very well known to people working in Riemannian geometry. Yeah, but yeah, even it's not so popular in the information geometry. Yeah, but I still think this is a very useful concept. Okay. Yeah, I think I finished my talk, and thank you very much. Thank you very much for your attention. Thank you. Okay. Do you have any questions? Yeah, so I think I think this Frobenius statistical manifold could be a good subject for future study. Like some non-trivial examples to find a Frobenius statistical manifold that is not parallelizable. And yeah, we don't know this is we don't know such example. Yes, such example. Yeah, but if we only have Euler characteristic of zero, then I think we have so we have these kind of examples. Yeah, but for this one. Yeah, so I think that when Dubrovin defined these Frobenius manifold, he introduced this concept for some physical considerations, because Frobenius manifold are mainly used like for mirror symmetry and also in the quantum cohomology. But actually here we just relax the condition 1, 2, 3, 4. We do not need these conditions. Yeah, but of course 3 is the one embedded in the definition of statistical manifold, right? We only require to have this is statistical manifold to have a Frobenius structure on its tangent bundle. Now, so we do not need a 1, 2, 4. Okay. Mm-hmm. Yeah, so another question is that this K structure, when K equal to 0 means WDV equation. So very natural question, we can study when this K is a constant. And so means the KK structure is a constant. And this is a kind of generalization of WDV equation, right? Yeah, so so this is still not solved, right? So for constant, so how to classify the manifold with constant sectional K-curvature?